Welcome to this video on experimental methods for science and engineering students. By working through an experiment, we'll draw out some of the terms used by measurement experts. Measurement experts are referred to as metrologists. Metrologists design and maintain measurement systems and are often found working with scientists and engineers on their measurement problems. Metrologists are in fact experts in metrology. Metrology is the science of measurement, not to be confused with meteorology, which is the science of weather and climate. Metrologists are employed by national organisations with titles such as National Measurement Institute. These organisations are responsible for many aspects of measurement, including the maintenance and development of measurement standards. Let's explore some measurement issues through consideration of a particular measurement situation. Here's a block of copper. In my experiment, I intend to determine the density of this copper block by measuring both its mass and its volume. We can write the density as follows. Rho, which is a symbol we use for density, is mass divided by volume. M here, that's the mass of the copper block, and V is its volume. Metrologists refer to quantities that are to be determined by measurement as measurands. And as in this experiment we want to find the density of copper, the density is the measurand in our experiment. I'm going to measure the dimensions of the copper block using these vernier calipers. Here's my block. And from the dimensions of the block I'll be able to calculate the volume. So let's just do a sketch to show the situation. Let's call that dimension H, that one B, and that one L. So the volume is going to be H times B times L. So I've measured H, B and L using the vernier calipers just once each, and I got the following. H was 25.11 millimeters, B was 25.70 millimeters, and L is 25.09 millimeters. Bringing this all together gives me the volume I can express in millimeters cubed as 16191 millimeters cubed. I'll also express it in meters cubed, which is 1.6191 times 10 to the minus 5 meters cubed. I use the top loading balance to measure the mass of the copper block, and here we see the mass is 145.78 grams. The balance will measure mass to the nearest 0.01 of a gram, so its resolution, in other words, is 0.01 of a gram. Now we can calculate the density of the copper block. Density is mass over volume. The mass of the copper block in kilograms is 0.1458 kilos, and the volume is 1.6191 times 10 to the minus 5 meters cubed. This will give us our answer for the density in kilograms per meter cubed, and it comes out to 5 significant figures is 9003.6 kilograms per meter cubed. The density of copper given in the Handbook of Chemistry and Physics is as follows. Density of copper is 8960 kilograms per meter cubed. Now this value is roughly 0.5% less than the value that I obtained through my measurements. So far I've made no mention of error or uncertainties associated with the measurement of length and mass. Let's consider these before returning to the determination of the density of the copper block. How is measurement error defined? Here we turn to the International Vocabulary of Metrology, abbreviated to VIM. This is a document recognized internationally as the authority on terms used in metrology. This is what the VIM has to say about measurement error. Measurement error is equal to the measured quantity value minus the reference quantity value. If we take the reference quantity value to be the true value, then we can write the following. The error, the measurement error, is the measured value. So this is our error here. The measured value is what we do when we make measurements with our instruments, minus the true value. The true value of any quantity is elusive. It is the value we'd obtain if we could eliminate anything and everything that could influence the measurement we want to make, and that the thing we are measuring is not changing. If it is changing, it's hard to imagine that there is a true value. In the example of a copper block, this means we'd need to hold the temperature of the block absolutely constant and possess vernier calipers that could measure length perfectly, e.g. there would be no limit to its resolution. None of these things are possible, so the true value cannot be known exactly. As the true value cannot be known, it follows that the error cannot be known exactly, and therefore we can't put a number to the error. So what we'll do is we'll move on to consider measurement uncertainty, which can be established and a number can be put to it. So what does VIM have to say about measurement uncertainty? The measurement uncertainty is a non-negative parameter characterizing the dispersion of the quantity values being attributed to a measurand based on the information used. We can write that the true value of the measurand lies with a given probability in an interval given by the following. The interval containing the true value of the measurand is the best estimate of the measurand plus or minus the measurement uncertainty. The still seems rather long-winded, so let's say it a little more tightly. The true value is the best estimate plus or minus the uncertainty. On the right hand side here, we're really defining an interval in which we expect to find the true value with a particular probability, which we'll come back to at some later stage. Returning to our mass and length data, I made only one measurement of each of the quantities of H, B and L and the mass. Now that's not good practice, as there are many reasons for repeat measurements to show some scatter, such as temperature fluctuations affecting the dimensions of the block. Nevertheless, as I only took one measurement of H, B and L, there has to be my best estimates of these things, and they were as follows. H was 25.11 millimeters, B 25.7 and L 25.09, and the mass best estimate is 145.78 grams. The uncertainty in each of these values will contribute to the uncertainty in the density. But what is the uncertainty in each? Well, there are several contributions to uncertainty, but we'll just consider one, and that's due to the resolution. So the resolution of the lengths can be considered to be the last digit that we see here, so that we can measure height or H to 0.01 of a millimeter, likewise B and likewise L. So H, I'm going to use U to represent uncertainty. So uncertainty in H is 0.01 millimeters, in B likewise, and in L likewise. The mass can also be measured to 100th of the unit, and the unit here is the gram. So the uncertainty in the mass is 0.01 grams. Now we need to bring together the uncertainty in the various quantities and the best estimate of the quantities into an equation which will give us the overall uncertainty. I'm not going to prove this, but the equation for the fractional uncertainty in the volume, this ratio of the uncertainty in the volume to the volume, is called the fractional uncertainty. Is given by this equation. So we have the fractional uncertainty in H, which is UH over H squared, plus the fractional uncertainty in the length B squared, plus the fractional uncertainty in the length L squared. All these things added together and then taking the square root. Well, not only do we need the fractional uncertainty in the volume, but we also need preferably the fractional uncertainty in the density, and that's given by this. So here we have fractional uncertainty again, but this in case it's a ratio of the uncertainty in the density divided by the density, and it's given by the fractional uncertainty in the mass squared plus the fractional uncertainty in the volume squared. This is going to come from the first equation, once we've put in all the numbers that we have for the uncertainties and the best estimates, and this will give us the fractional uncertainty in the density. Now, once we put the numbers in, we get that the fractional uncertainty in the density is 0.000688. We can rearrange the equation, just bringing rho to the right hand side, so that the uncertainty in the density is the density times 0.000688. Now we know the density, calculated that earlier on, and so multiplying the density by that 0.000688, we get 6.2 kilograms per meter cubed as the uncertainty in the density. So we could write the true value of the density is 9003.6 plus or minus 6.2 kilograms per meter cubed. Now we could round this uncertainty here to one significant figure to make it 6, and then we'd have to round this to 9004 to have the same number of decimal places. But we'll keep it as it is. You can use one or two significant figures. If you subtract 6.2 from 9003.6, you get the lower end of the possible value the true value could be, and then you add the 6.2 and you get the upper end. So we are reckoning that the true value is likely to lie between these two limits. Let's look again at the density given in the Handbook of Chemistry and Physics for the density of copper. It's 8960 kilograms per meter cubed. What I obtained through the experiment was an interval for the true value of 8997.4 to 9009.8 kilograms per meter cubed. If you look at the handbook value, it does not lie in this interval. So why could that be? What might be the reasons? Well, let's have a look at some of them. The face of the copper block will not be perfectly smooth, so there will be variations as you work your way across any particular part of the block. The opposite faces of the block will not be perfectly parallel, and if you were to move from one edge of the block to the other, you'll probably find that the dimension, the HB and the L, would change slightly. The reference temperature for the handbook is 20 degrees Celsius that is given for the density of copper. But in my experiment, I was holding the block, so the temperature would be varying. As the temperature varies, so does the expansion and contraction of the block. And so I will not be making my measurements at 20 degrees Celsius. That will be a cause of uncertainty. Also, there's no information given about the purity of the copper. I assume that the Handbook of Physics and Chemistry is referring to high purity copper, but I have no idea of the purity of the copper on the block that I was interested in. The instruments, the question is, have the instruments been calibrated recently? If they're not, then they will be a source of uncertainty. And the accuracy of the instrument will be stated by the manufacturer, and it's likely to be greater than the resolution of the instrument, and that wasn't taken into account, and it needs to be. So the uncertainties would be bigger than that I used in my calculations. Lastly, the experimenter would have limited skill and experience, possibly, and that would impact on the uncertainty, and that's true with all experiments. This video considered measurement error and measurement uncertainty, and emphasised these two things are not the same. Terms used in metrology, which are unfamiliar outside the world of metrologists, were introduced, such as measurand. Quantities were measured that allowed for the determination of the density of copper and the uncertainty in that density. An interval was calculated within which the true density of the copper would lie, with a given probability. But how do you calculate that probability? We'll tackle this issue in another video. Until then, goodbye for now.